friends, I'm back again, Dr. BC here once more with another video on quantum mechanics. I hope that my early videos are watched by you and you have some useful things from those videos. Don't forget to comment on those videos as well as put some suggestions for further improvement of the videos. So let's start with this video, and this video will be particularly on Gaussian packet. From the last video we learned that Heisenberg instantaneity principle, where we took two functions f1 and f2, and for particular constitution that del x into del p is equal to a squared by 2, that equality sign comes into effect, that particular wave packet represents wave Gaussian packet. And from that considerations, we'll talk about Gaussian packet. What is the wave function representing it, and what are its different properties? So let's go on. So let's recall back these things, as I just said it here a few seconds back, that f1 is equal to the function of f1 and f2 are just multiple of each other, and the condition that del x into del p is equal to a squared by 2 is the condition where we can talk about Gaussian packet. So let's recall back equations 1 and 2, that particular functions that we defined in the last video, and then we just go for the definition of Gaussian packet. But product of the uncertainties in position momentum is unique. That what it says that del x into del p is equal to a squared by 2. So this condition is what represents the Gaussian packet. Now when this condition is satisfied, del x into del p equal to a squared by 2, that f1 becomes a multiple of f2. And since we have equation 1 and 2 already, and with 3 we have these equations. I squares del x is equal to icx del psi. So 4. Or since it's a one-dimensional case, so we can replace this partial differentiation by equal differentiation, and some simplifications make it like this: del d psi by d psi is equal to minus c by squares x dx. So it's in an integrable form right now, and if you integrate this, as we know, dx by x integration is equal to log x. So similarly here also, this would give us log psi, and this would give us c by yj equals x squared, because c and is a constant and some integration constant k. The simple integrations are here, and then we have the k can be determined from this. We can determine k, or particularly we find it as involved in numberless constants. So if we take the exponential equation and the last equation, that is this one, log of sine equal to minus cx squared plus k. If you take log, then it will become like this. This one, sine equal to e to the power cx squared by x squared plus k, and then it is e to the power k, and e exponential to the power minus cx squared by x squared. And then finally, we can represent this e to the power k as normalized constant, and we are living with equation 5. Psi equal to n e to the power minus alpha squared into x squared. Where we put alpha squared is equal to nothing but this constant is c by twice this cos. So we have now a standard form of the wave function for the Gaussian packet, and is given by equation 5, where n is normalized constant coming from this constant integration constant k, and alpha squared is another parameter which is in terms of two constants c by twice this cos. Now this normalization can be done as usual, that modulus of psi squared is equal to 1. If you do these things, this particular will lead to this kind of integrations, the limits are minus infinity plus infinity, and to put some simplifications, that twice rho 2 alpha x is equal to y, and then dx will become dy by rho twice alpha, and this 6 will become n is equal to twice rho 2 alpha, and integration will be like this. So we have the integration, we have e to the power e squared dy, and since this is a standard integration, e to the power minus y squared dy to rho y, So ultimately, we after doing some simplifications, we are living with n equal to y alpha square by pi to the power half. So the normalization constant is determined for some standard integration process and the normalization process as discussed earlier. This is the integration there we must remember. So this is the normalization constant given by equation 7. So bring the value of n from 7 in back in equation 5, we will limit this wave function. That wave function for a Gaussian vector is psi to the power alpha square by pi to the power half e to the power minus alpha square by x square. Now this alpha can also be determined, and this can be determined from taking into considerations of those definitions used in statistical point of view while deriving that uncertainty. These are the relations that we already discussed about that uncertainty in position can be like this, and this is the expectation value, this is given by equation 10, and putting the particular case when then del x expectation value of x is equal to 0, we have this thing, del x is equal to expectation value of x square. This is also a special case taken in the last video also while deriving that uncertainty. So 8 and 10 will give us this one. If we put back this 10 in equation 8, then we have this equation. Del x square is equal to this because this expectation value, and ultimately after doing all these integrations, just like in the last slide, where this is a standard integration, whose value is pi by square root of pi by plus alpha square to the power half. And we are left with alpha equal to 1 by 2 rho x. So alpha is given by special width. That means the special expansion of that or the uncertainty in space. That is del x, the special variation you can say. And since alpha is determined here, we can go back to the earlier equation also. So we are now left with a very well-known form of wave function for a Gaussian vector, where we have determined already a normalization constant in terms of alpha, and now this alpha is given in terms of uncertainty position or expression with del x. This particular equation. So with this, we are left with a Gaussian wave functions, and which can be represented from two figures. This A and B, we can see that this is the figure where that Gaussian wave function varies, and putting different values of alpha, you can see that how the Gaussian wave function varies. This is for large alpha, and this particular solid is for small alpha. And we see that we can notice few things from this diagram, and then discuss these things like this. And these are the things that we can discuss. In comparison to other wave vector, Gaussian wave vector is easy to understand, or you can say the mathematical convenience is there because it converts with the product of minimum uncertainty both in position and momentum. And this is number one. And the second one is that it is the maximum value at x equal to 0 as depicted in figure 1, and its value is given by psi equal to 2 alpha square by 1 by 4. And then you can see how the amplitude of the wave function varies with alpha. You can see there that at alpha, large value of alpha, the wave function is sharp, and for small value of alpha, the wave function is flat. And then number 3, at x equal to 1 by alpha, we can give, when we put this in the relation expression for wave function, we find that when x is 1 by alpha, psi is equal to 1 by e, this value. So that means that it is 1 by e of the maximum value. At a particular point x equal to 1 by alpha, that wave function has a value of this, and this value is the maximum value of wave function. And number 4 is that the larger the value of alpha, the smaller is the uncertainty of the particle and vice versa. That means that as we see the expression for alpha, this one, if the alpha is large, then definitely del x is small. Then del x is small means the uncertainty in position is smaller. So more alpha, lesser is the uncertainty in position. This is one very important information. And also in that case, uncertainty position is minimum. Becoming minimum means that moment uncertainty momentum is increasing. So momentum increases, uncertainty momentum increases as it is inferred from Heisenberg uncertainty. So this one. So large alpha, smaller del x, but large del p. So large uncertainty momentum. So number 5, when alpha tends to 0, del x tends to infinity. And this is another one that 4 and 5 are almost same. Only the opposite things, contradictory things. And del x tends to infinity means that Gaussian function becomes flat. It is obvious from figure 1 also that lesser the alpha, greater is the flatness of the wave function. So ultimately when this alpha tends to 0, del x tends to infinity, that means that uncertainty position is very large. The particle will be confined to a very large region of space, and in that case the wave function will be a flat line. And on the opposite sense that if alpha is large, then del x will be small, tends to 0, and the Gaussian wave function will be sharper. So with this, we'll have done the assessment. This kind of assessment for us. What is the Gaussian wave packet and the wave function for it? Then the graphical variation of wave function, this is depicted in the figure 1, and how we explain on different parameters like alpha, and then some properties of Gaussian function that's discussed in the last slide. There's a high numbers of properties. So to conclude that Gaussian wave function is a very simple kind of wave function as compared to others. Wave packet as compared to others is because it leads to the minimum product of uncertainty in position and momentum. And the expression for wave function can be derived from our earlier consideration of statistical derivation of uncertainty principle, where we consider two functions f1 and f2. And that particular case when del x into del p equal to h crossed by 2, that equality sign preserved there instead of the inequality sign. We get the Gaussian wave functions, and in that case that f1 function is a multiple of f2 function, and with those mathematical kind of things we can get that wave function for Gaussian wave packet like this equation 1, 2, 3, 4, 1, 2, 3, 4 are the equations, and then the normalization procedure can be applied here, and we get the normalization constant given by 7. And that normalization constant is in terms of alpha, and then the alpha can also be determined in terms of uncertainty position as given by these equations. So everything is very fine while calculating this wave function or considering the Gaussian wave packet. And also the properties of Gaussian wave packets can be discussed, and these things really gives a very important information regarding Gaussian wave packets, and we can, in a little course of time, we can use the Gaussian wave function concept in establishing many things in the coming course of time. I think that this video will be helpful regarding the Gaussian wave function and Gaussian wave packet, and how to deal with the Gaussian wave packet, how wave function can be formulated, and all those things, and how the different parameters define, and what are different properties that the Gaussian wave packet carries with. And hope that you enjoy the video, and don't forget to comment on this and put suggestion on this, and hope to see you in the later course of time. Thank you very much for watching.